Okay, good evening. This is Professor David J. Delosreyes. Okay, it's October 17, 2023. The time is 11:12 p.m. Okay, my topic for this evening will be a continuation of my alternating current machines long video format lectures. Okay, okay, let's proceed. The subject matter for this evening will be alternating current machines, lesson number 41. We are running smooth. The title of the topic will be an example open delta transformer connection problem. Okay? A problem on the connection open delta. Or at least we have studied the last time around the concept on how to compute for the total power that could be carried by a closed delta when it happens that one of the transformers are actually damaged. So it will be operated as open delta. So the problem is asking what will be the total load that could be carried by an open delta, an actual real problem. Okay, I will try to read the problem. 325 kVA transformers are connected closed delta, meaning a delta-delta. Letter A, what total kVA can the bank deliver? Okay, the total apparent power. It's a closed delta originally. Letter B, to what kVA, meaning apparent power, should the load be reduced if one of the transformers is removed so that the bank operates as open delta? That's why I told you the subject matter for tonight will be an open delta connection. Okay? And how an open delta carry a percentage of the load. What will be the percentage? Okay, let's try to bring out the figure. Originally, the connection was a closed delta. Okay? And when it reaches letter B, one of the transformers is actually removed due to maybe, there's a problem. Okay, so they remove it. So it is necessary that power should still be delivered to the customer. So they operated the transformers as open delta. So for the given figure now, we are now on an open delta configuration, meaning the primary is open, the secondary open, one transformer is missing, and another transformer is missing. Okay, let's try to bring out the solution. We let capital letter S be the total apparent power that they could carry. Under the study of AC circuit, the total apparent power of AC circuit is actually S. And under the study of transformers, okay, it falls under AC circuit. So what is S under AC circuit will be S still under the study of transformer. So we let S be equal to the total apparent power that they could carry. Originally, the closed delta. So for a closed delta, the problem is asking what will be the total load that they could deliver or carry. Since it is a closed delta, the total apparent power that could be carried by each phase are actually the same. So if the problem is asking for the total apparent power, we will take the summation because we are given 3 kVA transformers, 3. And the rating of each is 25 kVA. So the total apparent power that could be delivered by 3 perfect delta connection transformer will be thrice, right? So it will be the apparent power of transformer number 1 plus transformer number 2 plus transformer number 3. So the total apparent power should be equal to 75 kVA. It is just a simple addition. These are just absolute values, guys. Okay, absolute values. because we are all talking total apparent power, so there will be no G part here. We are just taking the so-called absolute value of the apparent power. So the summation will be 75 kVA. So for a closed delta, if each is actually 25, no, 25, 25, and 25, the total apparent power that could be delivered by the tree should be 75 kVA. The next question. For an open delta, the problem is asking what will be the total apparent power S. Okay? So to compute for this, I will bring out one solution, one legal solution, plus the other solution will be the checking purposes solution. Okay, let's try to bring out the apparent power delivered by what you call this winding number 1 and number 2, considering the secondary side. The last time around, we derived this one, right? Right? Apparent power number 1 is kVA per phase times the cosine of 30 degrees plus theta. The value 30 degrees minus theta actually emanates from the difference of the voltage between the voltage and current. Okay, this current. So for the first one, it was actually 30 degrees plus theta. And for the second one, okay, it was actually 30 degrees minus theta. Okay. So this 30 degrees minus theta actually emanates from the vector diagram, right? It's the difference of the angles between the voltages and current. Okay. So for P1, winding number 1, if this is number 1, the total apparent power that could be carried by it was actually kVA per phase times the cosine of 30 degrees minus theta. For transformer winding number 2, it should be kVA per phase cosine of 30 degrees plus theta. Okay, since the power factor of the load is not given, okay, we assume theta to be equal to 0 degree. That's the simplest assumption that we could do. Okay, you can assume any value, it doesn't matter, but the simplest way to assume a certain value theta will be equal to 0 degree, meaning the load will be a pure resistance load. Okay. And the kVA per phase as per computation from A is actually 25, right? So if we now try to use these two equations here, substituting values, P11 will be 25 kVA, cosine of, when theta is 0, 30 minus 0 will be 30. And cosine of 30 is 0.866 times 25, that will be 21.65 kilowatt. This should be the total apparent power that would be carried by transformer winding number 1. For transformer winding number 2, the total apparent power is, true power is the 25 kVA per phase times cosine of, according to formula number 2, this will be 30 plus 0, right? But when theta is 0, this should be 30 plus 0. So this will still be 30. Okay? So this is cosine 30, so they will be the same. Actually, when theta is 0, actually that's the best condition for the two transformers, okay? Because they are not overloaded. Transformer winding number 1 and number 2 carry the same load. Actually, it's 21.65. This is actually the best condition for the transformers since they are connected open delta. If the power factor is actually 0, meaning the angle theta is actually 0 for a pure resistance load, that's the best condition for these two transformers to operate. Because at other power factors, okay, there will be a variation on the load that will be carried by transformer number 1 and number 2, like what we did the last time around, right? So the total apparent power now that could be delivered by the open delta will be total true power. Will be P1 plus P2, 21.65, that's 43.3 kilowatts. But the problem is asking for the total apparent power. So we'll go back to the formula. Power factor is actually cosine of theta, right? But cosine theta is actually power factor is cosine of theta, so we replace power factor by cosine of theta, it should be the ratio P over S. But for the given problem, the power factor angle is actually 0 degree. So S total now will be P total over cosine of theta. P total as per computation is 43.3 kilowatts over cosine of 0 degree. Cosine of 0 degree, 0 is a special angle, the cosine of 0 is 1. So this is 43.3 over 1. So 43.3 over 1 will be 43.3 kVA. So meaning to say, when they are operated delta, the total apparent power that they could carry is only 43.3 kVA instead of the 75 kVA. Right? It should be less because what do you call this? They are at the so-called negative condition because the other one is missing, right? But luckily, when theta is power factor, the load carried by number 1 and number 2 are actually the same, and they are both 21.65. At least one of them is not overloaded. Because there are angles or what you call this power factors in which the other one is overloaded and the other one is underloaded. But for a pure resistance load, the load carried by this in number 1 and number 2 are actually the same. Okay? Okay, let's try to check this 43.3 kVA. From the annotation on the concepts of open delta, like what I discussed, I think past 2 lessons ago, I place it on the annotation that the relationship, the open delta apparent power and the open delta closed power. This is closed delta, open delta. The relation is actually 57.75%. 0.57735 of the closed delta. I said this before, right? Because 1 over square root of 3 is actually 0.57735. Okay? So to check this 43.3, it will be 75. 1 over square root of 3 is actually 0.57735. And if we try to multiply 75 by 0.57735, it is actually 43.3 kVA. So what I said in the annotation was actually true, that the relationship for an open delta apparent power and a closed delta apparent power is actually the ratio of 0.57735. Okay, so if we try to divide this one, what comes out is 43.3 kVA. As you check, okay, this one here is equal to this. This is the long computation. Okay, but from our annotation, it says there the relationship is actually 1 over square root of 3, or that is 0.57735. So this is 43.3 kVA. Am I still on camera? This is 43.3 kVA. Okay, that's it, guys. That's the way how to compute for the total apparent power that the two windings could carry if they are operated open delta. Okay, good evening from Los Angeles. Professor David J. Delosreyes.